Good afternoon, and thank you for joining us today for our discussion on leading the charge, what innovation and the Inflation Reduction Act could mean for leadership in advanced battery technology. My name is Abby Wolf, and I am the Vice President and Director of the Center for Critical Mineral Strategy at SAFE. SAFE is a nonpartisan, nonprofit, mission-driven organization that is dedicated to securing supplies for our transportation, energy, and defense sectors in ways that support U.S. and allied security and economic competitiveness. As someone who studied geology and leads a critical minerals center, it may be a bit blasphemous for me to say that batteries are in fact at the heart of the current race to electrify. While of course you cannot make a battery without critical minerals, and critical minerals would not be buzzwords they are today without the batteries and subsequent EVs that they go into, but batteries are more central to the conversation that we're trying to have today. And the flurry of recent investments and commitments from businesses and governments alike to hit zero emission vehicle targets is currently the leading indicator driving the need for these mineral materials. While the U.S. is laggard in essentially all aspects of this connected supply chain, the Inflation Reduction Act, otherwise known as IRA or the IRA, has expanded the conversation beyond, will we be able to get the materials we need, to will we be able to build the batteries we need? And I might also add, who is going to build them, and does that matter? These points are especially salient due to some of the provisions in the law, most notably the 45X production tax credits and the 30D clean vehicle tax credits, which are designed to spur domestic and North American battery production and which have begun to draw the ire of some of our closest allies. Today's EV battery market is predominantly comprised of NMC, or nickel, manganese, and cobalt, and LFP, or lithium, iron, and phosphate battery chemistries, and dominated by China. According to the International Energy Agency, China produces 75% of all lithium-ion batteries and is home to 70% of all cathode production and 85% of all anode production. For LFP specifically, the number is even more stark. Some industry estimates place Chinese dominance of LFP battery manufacturing at more than 90%. The concentration in this part of the battery supply chain is staggering. And in order to make sure any of our investments in upstream mining and processing are worthwhile, we need to ensure that we have a diverse market for batteries and battery component manufacturing as well. So, can advanced battery technologies help us address expected supply chain issues for critical minerals and allow the United States and other relative battery newcomers to break into the battery space? Today, I'll be joined by experts from across the battery industry and value chain to help explore this question, including Selena Majkocic, Battery Technology Officer with Lyten, Kurt Kelty, Vice President for Commercialization at Sila Nanotechnologies, Michael Mayton, Director for EV Policy and Regulatory Affairs at GM, and Jessica Dura-Macholtz, a materials scientist at DOE's Resell Center at Argonne National Lab. Please note, we will be taking audience questions toward the end, so please have your questions ready and put them in the chat box. While we may not be able to address all of the questions in the time allotted, please feel free to reach out to us following the webinar for more information. And so with that, to get us started, and because this is such a technical subject, I'd like to invite each of our speakers to briefly introduce their organizations and tell us about their work in the advanced battery technology space and why they're central to our discussion today. So Selena, why don't we kick it off with you?
Sure. Hi, Abby. Hi, everyone. I'm Selena Majkocic. I lead the battery efforts at Lyten. I'm the Chief Technology Officer for battery here. And at Lyten, we are working on lithium sulfur batteries. Now, lithium sulfur is an obscure chemistry. It's been known for a long time, but it poses a lot of challenges, and people have kind of looked at it, but deferred from working on it deeply for quite a long time. We see work in the academic literature, but not an attempt at, or many attempts at commercialization. There have been some. Reason we're looking at this chemistry now is that it's very different, and it takes us into an entirely different space from a standpoint of supply chain. I come at this from about more than 20 years in batteries. I started working in lithium-ion batteries when these were small cells only used for consumer electronics. And then I worked at Tesla for a number of years. Kurt was my boss. He hired me into Tesla. And we worked together for a number of years, and we saw the evolution of a lot of lithium-ion cells as they became more and more capable, and our cars got better and better. Since then, I've designed battery packs, and I've worked, led engineering at Panasonic at the Gigafactory, and then did some work with in solid state batteries, and now I'm at Lighten. And you know, I've watched the evolution of the lithium technologies go for quite some time. And I think, you know, lithium sulfur is that next evolution. It's not an easy thing to do. It takes quite a bit of work. The chemistry has a lot of challenges to it, but it does give us an opportunity to get to a place of real abundance for cell making, where we are not constrained by some very limited mineral supplies. So that's why I'm doing this.
Thank you, Selena. Kurt, on to you next. And just for our viewers, Kurt just landed from a trip to South Korea, so he's a real trooper here. And thank you, Kurt, for joining us today.
Oh, I'm pleased to be here. Thank you. Thanks for inviting me. And yeah, it's so my name's Kurt Kelty, and I lead up the commercialization efforts here at Sila. What we're working on is a silicon anode material that replaces graphite. And what's special about it is, you know, silicon's been around for 15, 20 years. People have been talking about it. It's the next greatest thing. And it's been very difficult to commercialize, except for using 3, 4, 5% mixture in mixing it with graphite. And the primary challenge has been that it swells too much. And what we've been able to do is solve the swelling issue. We've been around for 11 or 12 years now, and we're actually shipping product to market. I've got a little Whoop fitness tracker on my wrist here. We've been shipping this for about 1.5 years now. And the advantage that silicon provides out there is a couple of points. One is the higher energy density, so we can get 20% higher energy density compared to graphite. And you can also get fast charge. So we're getting fast charge in our labs. We started focusing on this in the last year or so, and we've been able to reduce it from 20 minutes down to 10 minutes when you're charging from 10 to 80% of your vehicle. So with those two advantages, what we're hoping to do is get more buyers of EVs out there. You can imagine if you can get 20% longer driving range, and you can be charged up in time that's similar to what it charges, what it costs, what it takes to fill up a vehicle with gas. Your adoption rate is just going to continue to rise at a very rapid rate. So that's what we're working on here at Sila, and I look forward to sharing more of that with everyone today.
Thanks very much, Kurt, for that. Next, we'll throw it to you, Mike. Please tell us a bit about what you do and why GM is central to this conversation today.
Sure, Abby. Thanks for having me. So my name's Mike Mayton. I'm the Director of EV Policy and Regulatory Affairs for General Motors. My background is actually in product planning and electric vehicle planning. I've also been looking into the EV battery supply chains for the last 3 or 4 years. So at General Motors, I think it's no secret we have very ambitious plans to transform our company into an all EV company. You know, one of the nearer term targets we've put out there is we're going to have the capacity to produce 1 million EVs annually in North America by the end of 2025. That's a really ambitious target. To support that target, we've announced that we're building 4 battery facilities here in the U.S. To produce the batteries for our Ultium systems. So between those 4 plants that we've announced, those 4 battery plants that we've announced, that's about 160 gigawatt hours a year of lithium-ion battery production. Just a massive scale that we're looking for. Of course, the IIJA and IRA both provide really nice tailwinds. You know, those investments, by the way, were announced before the IRA, but it's certainly a nice tailwind that really gives a benefit And what we're really focused on right now is securing and fortifying the supply chain of materials going into that those plants. So we've been able to secure enough material to realize that 1 million unit target by 2025. But certainly, we're looking beyond 2025 at some of the longer term things as we look to increase battery density, energy density, decrease cost. And just overall, I would say make the process greener and cleaner as well. And avoid maybe some of the more dirtier raw materials. So to do that, we opened our Wallace Battery Innovation Center here in Warren, where we in Warren, Michigan, at our technical center, where we're not only looking at kind of the next generation of chemistries, kind of across the spectrum of future chemistries, but also, and I think importantly, we'll get into the discussion, how to make those chemistries at automotive grade at scale. And that's part of this journey we're on. Is it's one thing to make things work in a lab, of course. It's quite another to make them work at scale at 160 gigawatt hours per year, and safely and at high quality. So really looking forward to the conversation today. Thanks.
Thanks very much, Mike. And last but by no means least, Jessica.
All right, good afternoon, everyone. My name is Jessica Durham-Mockles. I am a materials scientist at Argonne National Lab and also part of the Department of Energy's Resell Center for Advanced Battery Recycling, where I am a focus area lead for the direct recycling effort. And the Resell Center is focused on improving recycling techniques that we have today, and getting recycling to a point where we can easily transfer it to industry. You've heard that OEMs are pushing to make their vehicle fleets all electric. So that means there's going to be a huge demand for batteries. It's been predicted that by 2030, the demand will be over tenfold of what it is now. So we really have to think about what's going to happen to all of those batteries when they come out of electric vehicles. And that's where we come in. Battery recycling in the US is still in its early stages. So the Resell Center has been funded to look at technologies that are being used today, but also new technologies so that we can improve recycling and make it more profitable. Because as we like to say, nobody's going to want to pay to recycle their batteries. Another big point about recycling batteries is that it has all these critical materials like lithium, nickel, graphite, and we rely on foreign countries for these. So if we take these batteries that we have in the US and extract the critical materials from them, we can really create a more robust domestic supply chain of critical materials here in the US. And the other goal of Resell is to really help DOE drive battery pack costs down to that $80 per kilowatt hour level that they're targeting in about 10 years. And we can help to do that by getting these critical materials back here in the US and putting them back into the supply chain. So thank you, and I'm looking forward to the conversation today.
Thank you very much, Jessica, and everyone for providing that brief introduction to your organizations and beginning our conversation on why we can't just be focusing on, NMC and LFP chemistries, but really need to be taking sort of a broader approach to battery chemistries. If we could maybe put a little bit of a finer point on that, because I think, when the general public looks at the media, when we look at headlines that are out there today, a lot of the focus is on these traditional chemistries. And I was just wondering, why is it so important that we don't just focus on those things and we also are, scanning the horizon constantly and planning for this new future of advanced battery technologies? Why should really people care about advanced battery technologies? Is it density? Is it recycling capacity? Is it, our ability to leapfrog in, in safety or something like that too? Selena, is it all right if I turn turn to you first to discuss this particular point, put a finer point on it for us.
Sure. Look, when we're kind of in an early stage of electrification, really. I mean, it seems like we've been doing this for a bit, but if you think about it, I mean, petrochemical industry, what, 100 years of development? Automotive has seen 100 years of development for the internal combustion engine, and we've had, a decade, maybe a little more, of electric vehicles. I mean, there's so much more to go. You wouldn't stop with, you wouldn't look at a vehicle that you had made or an internal combustion engine you'd made in the 1900s or the 1920s and be like, we're good, right? You would keep pushing. You look at this and you push to the new technologies. It's the same with batteries and electrification. There's so much opportunity out there. The chemistry that I'm working in with lithium sulfur, it has a lot of challenges to it, but at the same time, it has some really big potential benefits, which includes incredible energy density, an incredibly tractable supply chain. It also has, potential for really high safety and a very different approach to battery safety. So, that's super exciting. And that's something that can really help push us into the next generation of EVs. And, where I look at it is when we look at, are we good with just NMC and LFP? The high nickel chemistries rely on nickel. Nickel is in somewhat short supply. If you look at the number of gigafactories that have been proposed and you look at the world's nickel supply, you find out real quick, the two don't match, okay? And it's, nickel is, there's some challenges with finding more supplies of that and then extracting them. So, I think it's important to do NMC and CA right now and invest in it, but you have to think about, well, if I really want to electrify everything, I cannot just rely on the current chemistries because I just don't have the minerals for that. So if I want, to have everything electrified and all of us really enjoying our electric future, because that's part of it, right? I have to get to another chemistry. So that in of itself is a reason to look at lithium sulfur.
Thank you so much, Selena, for that response. Mike, I don't know, maybe if I can call on you next to comment on that. I love,
Sure.
Selena, how you said, 10 years, like we've achieved it, right? Like we're there. So how does GM feel about that?
No, I mean, exactly right. I agree 100% with Selena. We're, 10 years, 15 years into this, we're at, I say probably Gen 2.5 or Gen 3 of batteries right now, but we're frankly still not where we need to be from a cost and energy density, a charge rate, a C rate standpoint, especially for some of the more challenging applications, whether that's low temperature, meaning, below zero in Minnesota or whatever, whether that's for more energy intensive applications. So my example there is if you're in a delivery truck and you're hauling potato chips, an EV will go so far. If you're hauling soda pop, an EV is not going to take you nearly as far. So we're not where we need to be a substitute for ICE vehicles at equivalent cost for several of those applications. So we are absolutely in the early stages of this. We've tried to future-proof our Ultium platform as much as we can to accept a wide range of formats and chemistries, and I think that's really important. Because we know this is not a static, especially again, it's 10 years in, but let's be honest, it's only the last maybe 2 or 3 years where there's been this massive flood of money coming into this area too. So we really expect, a lot of great things in the next 10 years, a lot of, improvements to get us to that step function reduction in cost that we really need. Getting to those pack levels under $100 a kilowatt hour or under $80 a kilowatt hour, where it really starts to make equivalent financial sense to internal combustion engines for equivalent performance. And I think that's where some of these next gen batteries can really chemistries, formats, etc., can really help us out.
Thank you so much, Mike, and thanks for letting me put you on the spot. Kurt, I might turn to you next if you have anything that you'd like to add. Why is it so important to be focused on these advanced battery technologies? Mike referenced, we're still not quite there on cost, on energy density, on charge rates, et cetera. What are some of the benefits maybe of silicon anodes that, might help us overcome some of these challenges?
Yeah, Mike hit it right on. The 3 points here are cost, the charge rate, and the driving range, which is energy density. Those are 3 things. And we've got an adoption rate that's still tiny of EVs. I started working at Tesla in 2006, and so I've been working in this industry for a while, and like the others on the panel here, and we're still we're still at the early stages of this, and it's those 3 issues that come up. And it really pains me. Last week my brother-in-law bought an ICE. I just couldn't believe it. This is shocking. In my family, somebody bought an ICE. And it comes down to those 3 things. It comes down to cost and range and charge rates. And so we're doing at SELA is we're addressing all 3 of them. The first one is the energy density by increasing that by 20%. The second one is the charge rate by bringing that charge rate. You can imagine if the amount of time it takes to fill up a car with gas is 8 minutes. That's what the average time is. And we're able to get our charge time down to 10 minutes now in test samples. So we're gonna these will be on the market within that kind of charge time will be on the market probably 4 or 5 years if the chargers can handle it. Now that's a big if, because you got to develop the chargers as well to handle that. And then as far as the cost is concerned, we initially we're targeting the premium market. That's what we're going after, is that high premium market, upgrade packs initially, and then base packs for premium market. And one of the reasons is our supply is limited and our costs are high initially, but we have a roadmap to get our costs down below graphite at the pack level before the end of the decade. And at that point, there's no reason to use graphite. You've got a lighter pack, you got a smaller pack that can do fast charge. There's just no reason to use graphite. And then furthermore, we're American manufactured, and so you can get away from the China supply base. Our materials manufactured using hydropower. So it's green energy, or if you look at our LCA analysis, CO2 emissions, we're much lower than graphite. So there's just no reason you would use graphite. And so we're able to address those 3 issues that Mike raised. It's the cost, it's the driving range, and it's the charge time. Those are the 3 things we really got to nail.
Thank you so much, Kurt. And oh my God, I can't believe your brother-in-law bought an ICE vehicle. So this next question is definitely targeted at him. And, in response to that, I think that, a lot of people probably in the audience and in the general public sort of feel the same way. Maybe we're not quite there yet. They're feeling some hesitancy about this. So what can we do to make this advanced battery tech go faster, I guess, is sort of the biggest question that people might have. Perhaps you and Selena might want to comment on, what are the current opportunities and challenges to going from, the lab scale to commercial scale? What's a typical pathway for companies like yours that are trying to ramp this up quickly? And why does it take so long? Selena, maybe I'll turn to you.
Sure. Taking so long is kind of a relative term, right? When lithium ion was commercialized in like 1993 or so, those cells weren't like that exciting, right? If you looked at them now, you'd be like, meh, not good enough, right? They've been evolving and consistently evolving over about 30 years, right? So if you look at history, you go, well, if I'm going to let the mass market handle this and I'm going to do, a slow adoption, which is driven entirely by market forces, you've got an example there, about 30 years, right? Maybe 25. Okay. If you want to go faster, you have to do something different. Okay. And that's where governments decide to do something different than just rely on market forces. That's why things like the IRA are so important. That's why continued investment is so important. And people are saying, well, what do you need? What do you need to go faster? Well, mostly you need investment. You need money, and you need a lot of money, because these are very capital intensive businesses. Okay. When I look at this and I say, okay, I'm doing some cells and they've got some really great performance and I'm in a glove box. Great. I'm moving them onto a pilot line. Even a small pilot line, tens of millions of dollars. Okay, and so Lighton's gotten the investment on that. We have a small pilot line. Okay, that's something that the capital markets can provide, right? But a pilot line doesn't get you to EV scales, right? It gets you some sample cells and some early samples, not even late samples, right? So now you say, okay, well, what do I need? I need a bigger factory. Now, do you go from pilot scale to gigafactory? It's probably not going to work so well, okay? Unless you really, really have this technology worked out very well and you've got all the manufacturing capability. So if you want to go to that, automotive EV gigafactory scale where you're talking tens of gigawatt hours, hundreds of gigawatt hours, like what Michael's talking about, you probably want another stop in between there. You go pilot line and then you go to some kind of a smaller factory, which is development, where you're going to produce cells for a while. They're going to be, at some volumes that are comparable to what Asia produced for consumer electronics for a long time, right? So, you're talking about millions of cells a month rather than millions of cells a day. And when we start talking about EV production, you need to be in the millions of cells a day scales, right? So you're going from in a glove box, you're making 10 cells a day, you are cranking, okay? It's awesome. And you get on a pilot line, you make 100 cells, that's pretty darn good. You make 1,000 cells, you're cranking. You get to that mid-range factory, you're making, tens of thousands, maybe a day. That'd be really good. You get to the full gigafactory scale, large scale, millions of cells a day, maybe tens of millions of cells a day if you're really at those 100 gigawatt hours. That's the difference in scale, right? What does it mean? It means a lot of money, a lot of investment, and you use that money to fund your R&D, to develop your manufacturing plants, to develop your supply chain, to pay for all the scaling that happens at the suppliers too, because if I'm going to make 1 million cells a day somewhere, I got to have all the raw materials to support that. So you got to invest there as well. And then, you have to just put those factories in, you have to train the people. That takes time, that takes investment as well, right? I mean, but the good news is it only needs money. If you think about it, there's great news because the physics works. The science is possible. Now you need the investment. And it's like, oh my God, it's so much money, but at least it's only money.
Well, there you go. We've solved it. It's only money. And
I would add a couple things there, but I think it's largely correct. I think it's money, but it's also getting that money turned into things on the ground. And we see this with, just to make an analogy towards the infrastructure funding, the $7.5 billion. That's great that money's available. The first chargers aren't going to be operational until probably mid-24, right? So there's the money, but also the system to get it spent is important. And I would also highlight workforce, quite frankly, is what we're finding is frankly a bit of a challenge in this industry right now. It's just a brand new industry, right? Each of our plants is going to hire somewhere in the neighborhood of 1,000 to 1,500 workers. Finding that amount of workforce, in an area and in certain areas of the U.S. is frankly a challenge.
You got to find them, and then you got to train them. And that's a huge
retain them
and retain. But training someone, you go and you want to train them to make cells, right? You put someone in front of a giant coating machine or a winding machine or even a stacking machine, and they look at this and they're like, oh my God, right? You don't just, this is not, people like to think of manufacturing as I Love Lucy. It is not that. This is high tech. These are not, low-end blue collar jobs. These are advanced manufacturing jobs, which are, they're great. And as a nation, we want them, right? But this is where, when I say it's only money, it's a lot of money to invest in a workforce that can do that, because you've got to invest big time.
I want to come back to the jobs thing, but I want to bring Jessica into the conversation here a little bit as well. So Jessica, we've been talking a lot about, money as, an obstacle for some of these things. And I think that it's well known that money is also a huge obstacle for making recycling possible. As you said, people don't want to pay to recycle their batteries. We have to try to make this as easy as possible for people. Is Argonne in any way working to develop technology, new technologies to make it cheaper to recycle batteries, or, are changing chemistries, putting a wrench in those works and sort of making you look in a couple different directions at once?
Yes, so the main goal of the Resale Center is to make battery recycling cheaper. And I mentioned before that Argonne is leading the Resale Center, but we're really a collaboration with other national labs and universities. We work with Oak Ridge National Lab, Idaho National Lab, NREL, and 4 other universities from around the US. And we really try to bring scientists together from diverse areas so we can solve challenges related to recycling, and really try to address what the issues are. And so the problem nowadays is recycling is not profitable. So there aren't a lot of, before the IRA, there weren't as many companies investing in this. So the IRA was really great because there's been a lot of money for recycling, and getting people to start up their companies or go further into scale up and build out some facilities or pilot lines to do work. We're part of several projects that will be doing that. And that should be starting within about 6 months, where not only do we do research internally, but we try to help companies solve R&D challenges related to scaling up their recycling pilot lines. And right now we're focusing on the major chemistries that have been used in the past 10 or 15 years, because that's what we've been seeing come back now. So NMC, LCO, LMO, NCA, and more recently LFP. Those are all chemistries we see now and we'll probably be seeing for at least another 10 or 15 years. But we are really trying to keep an eye on what will be the next chemistries coming to market, because the technologies we're developing work really well with what the battery industry is using today. But if we switch to something like lithium sulfur or silicon or solid state batteries, we really need to reevaluate the technologies we are looking at to see if they'll work for those chemistries. Because depending on what form like sulfur is in, you won't want to put that in water because there are a lot of hazard implications when you do that. So we really need to see what's coming up next on the market. And then start developing those technologies early before these batteries start dying and reaching their end of life and going into recycling. So that's a big issue. And we're really excited to see where the battery market is going so we can kind of shift as needed.
Thank you, Jessica. I was wondering if you could go into that a little bit more, how you work with the private sector to help them move from sort of the lab scale, the bench scale, up through to commercialization. Are you able, without, naming any names or proprietary data, which I understand we need to be sensitive to?
Yeah, so we really try to bridge the gap between like academia and industry. So we're currently building out our own pilot line to do recycling, where we'll have a variety of operations that we developed. We like to call it the unit operation playground, where you can take these operations and put them end to end in a process and see what happens. So we want to make it really flexible for people who are working on all different recycling technologies. So there are 3 main ways batteries are recycled today. It's using hydrometallurgy, pyrometallurgy, or direct recycling. And Resale has 60 projects, over 60 projects that span all of those areas of recycling. And yeah, typically we work with companies through DOE funding opportunities. So the calls that are coming out with BIL funding or IRA funding, companies will typically reach out to us looking for help. So we have a website, resellcenter.org, where we get a lot of inquiries. We talk to companies and see how we can help them address their challenges. But as a national lab, if you don't want your proprietary data to be in the public domain, you can also work with us through things that are called collaborative research and development agreements, or CRADAs, where a company can come and pay us directly to help solve a challenge. But we do have technologies from the bench scale all the way up to the pilot scale, and we scale incrementally because scale up, the problem is it's not linear. So every order of magnitude you go up in scale, there can be issues that you have to fix before you go further. So that's the point of us, is to have this available for people to come and test out their processes with.
That is fascinating, Jessica, and I feel like I speak for everyone where I would love to come and visit your unit operation playground, because that just sounds like a whole lot of fun. I'm imagining a typical playground, right? But
a little more dangerous, but
that
it's
just
fun.
that adds to the excitement. So no, good, living life on the edge. So maybe I'll circle back to some of the workforce issues that were mentioned before. So, you know, we're going to need more expertise in recycling. We like to say it's safe that recycling and mineral processing for raw materials are also sort of like two sides of the same coin, using hydrometallurgy and pyrometallurgy sort of systems that you were talking about before. We need to get those workers in. Maybe I can turn to, you know, Selena, Kurt, Mike, a little bit to talk about, you know, what kinds of jobs are we talking about sort of at the end of the day? Maybe for Selena and Kurt, you know, compared to maybe some of the, you know, like the CATL, like gigafactory that like Ford is attempting to bring in, like what types of jobs, or like what might be the differences between the kinds of jobs that like Sela and Lighten might be providing versus, you know, like a typical gigafactory job, or maybe there are no differences.
Yes, so when I'll take a step first. We're going to be a little bit unique from the others here, because we're making a powder, and it's a bunch of engineers, but it's not a big bunch. I mean, we're talking, ours is a quite automated process. So our first phase is going to be less than 100 employees, and that's an EV scale factory. So it's a large scale factory that's doing double-digit gigawatt hour production. The equivalent of double-digit gigawatt hours. So it doesn't require a whole lot of people. That and we'll be ramping it up to several hundred people over time. And it is mainly engineers, and there are some operators in there as well. I do want to address partially the conversation we were just having on why is it taking so darn long to get lithium-ion battery, or the new technologies to market. I just want to emphasize a little bit more, like what Selena was saying, all these different steps that you have to go through, these different factories, and we're already on our third line right now, our third factories, if you might want to call it that. Our fourth one's going to be in Washington, starting in 2025, which is the first real mass production factory. It takes time to get to that point. And that's the first time we're actually going to be supplying into Mercedes for their G-Wagon that they've already announced using our material. But the reason that one of the other reasons it takes so much time is that to test a battery, you've got to put on cycle, and it takes like 3 months, 6 months until you get results back. It's very different from any other, most any other material that's being developed, like a chip. You make a chip, you put it on test, at the end of the day, you know, did it work, did it not work? With batteries, you put it on cycle, you find out 3 months later, 6 months later, oh, it worked or it didn't work. And if it didn't work, then you got to go back to the beginning and start over again. So it's a really long process. The iterations just take forever. So that's one of the reasons why it takes so long. And as everyone else says, it does take a lot of money. We've been really fortunate. We've raised almost $1 billion, I mean, more than any other battery material company ever. So we've been fortunate in that, and DOE's been really helpful for that. They've invested, well, they've granted us $100 million in November for our factory up in Moses Lake in Washington. So that's really helpful in that scale up, and that money, as Selena and as Mike said, is really important, and DOE is being very helpful there for us.
Thank you so much for that perspective, Kurt. Mike, maybe I can bring you in a little bit here too. You know, Kurt and others have talked about how the bipartisan infrastructure law, how IRA, how different government programs have been helpful in, you know, scaling up these technologies. But I'm curious, you know, what role do downstream companies or OEMs play in supporting battery startups? You know, what role, if any, should you be playing in trying to help commercialize or ramp up these technologies?
Yeah, so you're right about the IIJA and IRA. We provided several letters of support to various companies in the first round of IIJA funding. You know, because we think that there's so many promising technologies out there. I think what we can do is you know, kind of guarantee the demand for those products, provided they work. I think that's kind of the big thing, right? We're not going to commit to buying something that is still, you know, very early in the R&D stages, but where we can help, we can almost, you know, again, provided one of these materials works in our future battery chemistries, we can provide that scale, provide that volume, provide that guaranteed customer that they need to be able to say, hey DOE, we have this product, and if it works, you know, we have this customer lined up that we're working with. So we're working with any number of companies in their early stages to you know, help them qualify their material for you know, introduction into our supply chain. So we're working, I would say, at literally every step of the supply chain, from the extraction all the way up. So I think, you know, companies like ours can just provide that. It's basically immediate scale for some of these companies, and immediate guaranteed scale that they need to kind of solidify their business plans and then get the money from the DOE.
Thanks, Mike. If I can keep it on you for a little bit longer, we're seeing more OEMs enter into joint ventures with big established battery players. I mean, of course, you guys have your joint venture with LG, Ford has SK, perhaps also CATL, Tesla, of course, with Panasonic, and I'm sure there are others that I'm also forgetting. But I'm wondering maybe if you could comment a little bit on, you know, what are the differences between working with, you know, a big established battery player, and what are the risks in associating with some of these smaller startups, recognizing that there are risks in dealing with brand new companies. And, you know, is there a role for government maybe to come in and to help de-risk some of those relationships?
But potentially, I would say, you know, in my opinion, the reason that larger companies have gone the JV route is quite frankly, it's all about speed. These companies are really the only proven companies who can make these batteries at scale, at the quality we need, with the energy density and the cost we require. So, and frankly, there's really only a handful of them that exist really in the world. I think we can count them probably on one hand right now. So I think it's a way for GM and the rest of our colleagues in the auto industry. We're not battery makers, right? We did not. We were engine makers. We were transmission makers. We don't have a lot of expertise in this area. So in order for us to gain that expertise as quickly as possible and create that scale, and again, maybe in the automotive world, we're moving at light speed, right? In this transition. We were, you know, the joint venture route was really the way to go. But what I can say is, you know, through these joint ventures, at least GM, we're learning a lot. We're learning that it's not just about the chemistries, it's about there's trade secrets, there's IP in the manufacturing processes too. So I think that'll help us in the future, as, you know, I think in the future, quite frankly, we'd love that IP. Whether it's the chemistries, whether it's the trade secrets on the manufacturing process, we'd love that IP to be generated by us here in the US or our partners. And, I think the government can help support that in terms of a long-term strategic plan. So like I said, when we open that Wallace Battery Innovation Center here in Warren, it's not just a bunch of scientists with Erlenmeyer flask looking at the chemistries and the button cells and everything else. We're looking at the manufacturing side of things, the manufacturing processes, the things that Kurt and Selena have been talking about, and I think that might be missing a little bit from the public debate right now. Is it's not just about the chemistry; it's about making the cells in the formats at scale, which, as Selena indicated, is literally the millions of units a day rate.
Yeah, if I could talk a little bit about this, what's different between an established cell company and a startup? If you have an established cell company somewhere in the world, you have a factory that's producing at least commercial scales, consumer electronic scales, right? I would call this like there's a home factory somewhere, okay? And in that home factory, you are doing your manufacturing development. You may be trialing new chemistries, but out of that home factory also, you can produce the sample cells that you're going to send to an OEM, right? So let's say you're contemplating working with an OEM. They want some sample cells, and then they want a lot of sample cells, okay? To do a final sample run for a big OEM, they want like 100,000 cells, okay? And that's a small number. They may want more, right? Now, here's the trick, okay? They're saying, okay, well, we want a gigafactory that's going to produce at our scale, but you got to produce these sample cells at rate somewhere to get that gigafactory like approved, right? Well, okay, so if you have a home factory, you make those cells at your home factory, you ship them off to your customer, and then you're building your gigafactory as you're going along. And by the time they go into production, because they'll spend at least a year testing those cells before they'll give you the buy order, right? So while that's happening, you're still building up your factory, okay? Great. And by the time, and if you time it right, by the time they're ready to buy, you've just got all your equipment cranked up and your people working, and you start producing cells. Now, that means you have to have had that factory to deliver those cells. Otherwise, what are you going to do? You're going to go build a gigafactory. You're going to run 100,000 cells, and then you're going to idle that factory while you wait for your OEM customer to test those cells. There's no way the economics works at all, right? So you have to have that mid-range factory somewhere, or you have to have another gigafactory. You have to have a factory somewhere just to get into the game, okay? And that's one of the biggest differences. If you want to ramp startups in the United States, you have to support that intermediate scale somewhere. And that means investing the capital for that intermediate scale. Because then, later on you say, okay, I want to do a JV with a big OEM. You've already got something that's producing at scale. You've got that place where you're making the sample OEM, and then you're building that other factory. But if you don't have that intermediate factory, you can't even begin those samples. That's where the government has a huge role to play, is funding that intermediate scale.
I want to get to one more question before we turn to some of the questions that we're getting for the audience. This is something that, we at SAFE, and I think in the general discourse, are sort of trying to think through when it comes to wanting to support, domestic late stage and startup, battery makers, while also working with, trusted allies, the big guys, like Panasonic, LG, and SK, with the speed and the scale to ramp up batteries. But I'm curious, Selena and Kurt, what is that dynamic like for you guys? Is it better to have more of those, big players, around as well? Does it, all rising tides raise all boats kind of a thing? Or does it also, suck the oxygen out of the room, so to speak, and make it a little more difficult? But of course, competition is always a good thing, right? And in the United States, we believe in competition, but curious if you'd like to comment on that at all.
I don't know. It depends on how I'm feeling on any other given day. How about you, Kurt?
Yeah, well, it also depends who's in the audience. It depends on that too. I'll share my honest personal opinion on this. If we having more cell manufacturing in the U.S., regardless of nationality, is helpful for our industry. I think because we get the supply chains that'll come here with that, we get the labor pool that's going to be trained on it, we get the capex investment that's going to go into it. So I know we're trying to prevent other countries from being here, but if we can get these companies here, it is a huge win, I think, for the U.S. and for us. And we're supplying our material works with any kind of cathode, it works with any kind of form factor, and so it doesn't really matter. We work with all of them. So I'm just getting back from Japan and Korea, and Mike had his list. You can count them all on one hand. Well, those are the ones we visited. So yeah, I mean, there's a limited number of companies out there, and they've got to buy from companies like us because we make the best silicon material, and so they're opening their doors to us, and they're happy to talk to us. But if you haven't proven that before, and as Selena says, if you don't have any kind of a factory really to make it in a scale that they can use, I mean, it's one thing to make gram scale, and Mike talked about this earlier, going from a lab scale to production. It's totally different. I mean, lab scale, you can make grams, great, and anybody can do that. There's so many groups out there that can make just fabulous material at gram scale. But when you go to that the single digit kilograms, and then the 3-digit kilograms, and each one of these is a huge step, and that's why for us, like the idea of shipping to Whoop, being in market for a year and a half, is huge, because we have gone from that lab scale to mass production. We've gone through all of those hurdles. Now there are some bigger hurdles ahead in going to the scale of EVs. That's another huge scale. And so, but we have a factory now that makes megawatt hour production. And so, as Selena says, you need to have that kind of material to get that validation started. But even then, once we get our mass production facility up in Moses Lake, when that's running, you still have to do validation again. It's the last iteration of it, to repeat it one more time. But for that reason, you need the capital, you need the patience from your investors. But yeah.
Yeah, I'll agree with Kurt. I mean, it's kind of like, oh, damn it, I want to be building that next gigafactory, right? I want all my factories all over the US. Totally want that. But the reality is, as Kurt has said, that every factory that comes in brings with it some benefits for the nation. The other thing to keep in mind is we're just starting out in the scale of these things. Okay. If you look at the scale of our petrochemical industry, if you look at how many rigs are out there drilling, how many refineries are out there refining our petrochemicals, if you look at just straight up how many gas stations are out there and how many pipelines to transport all this material, that is the scale of infrastructure you need to actually electrify all our vehicles. In electric cars, it looks a little different, okay, because you're not, producing fuel for that sort of thing, but you're replacing that with a whole different technology. So all of the raw materials supply, all the equipment suppliers, even the people who are servicing you on that equipment, it's helpful to have them in this country, right? You start off and you say, okay, I'm going to be making cells, and I've got to slit electrode, right? And I've got to cut electrode down. So I need slitting blades. I need slitting blades sharpened somewhere. Okay. Are there any shops in the area that can sharpen a slitting blade? Do they even know what a slitting blade is? Right? Well, the first time you show up at a machine shop and could you sharpen this? And they look at you, they're like, I don't know, what do you need? Right? Maybe. Right. But I mean, all of that infrastructure has to come into place, right? So the fact that there are people that are putting that infrastructure into place right now and beginning that process only helps us.
Thank you. So now maybe we'll turn to some of our questions from the audience. This question comes to us from Dominic Matthew. Dominic asks, and this one might be for Mike, I think, how integral is battery tech research / evaluating battery supply chain in the business lines of companies now? Is it still a separate vertical within companies, or is it being integrated into business strategies of companies? So essentially, how important is, battery tech and evaluating the supply chain for you guys right now?
I would say it's firmly integrated. I can say, so we've moved from, probably 2 people working in purchasing for EV raw materials to a center of expertise with about 100 people in it. with experts in lithium, manganese, nickel, right? But also looking at those future chemistries. So I think for us, we have certainly we're looking at securing that supply chain in the near term, but we also have a future group, right, working on looking at what are those next gen chemistries, what are the supply constraints for those. So I would say, as Selena indicated, this is a wholesale transformation, and we're again kind of changing the fundamental structure of our business to look at it that way. But yeah, I would say our research labs are and that handoff eventually to the supply chain, we're pretty tightly integrated today. And I should say it's also, with a nod to Jessica, the recycling team is because you can't talk about recycling without talking about battery production and cathodes. There is no recycling discussion without where the material's coming from and where it's going to. So it's kind of all of the above as we look to kind of transform we're transforming our products. I would say internally, we're also transforming our company from a structural standpoint to recognize kind of the new reality of the supply chains going in.
If I could add just one thing to in Dominic's question, just another tag on to what Mike was saying, but I spent a lot of time dealing with the OEMs. I was in Europe 3 weeks ago, and just one after another. And one of the things that they're finding over time is that those companies that have a chemist that is reporting to the CEO have so much more understanding of the market and capability to make the right decisions. That's what we're finding, is that if you have somebody that understands chemistry that's interfacing directly with the CEO is huge. And those that have a separation, we got multiple layers between that chemist and the CEO, are not making the right decisions today. I think that's a really critical element, having those people in the room.
And from an overall future planning standpoint, you end up having to make an assumption about the percentage of the U.S. market that's going to be NMC, because are there going to be supply constraints and price fluctuations? You have to, whether you're frankly planning on alternate chemistries or not, right in the near term, you have to look at that future and try and understand how much of that future is, call it NCM, NCMA 811, whatever you want to call it. How much of that, how much of that U.S. car market is that, and how much can some of these other chemistries maybe absorb some of that electrified market? And there's a lot of assumptions that go into that. But again, regardless of whether we're actively sourcing that, you have to be looking at that for kind of future commodity pricing reasons.
Thank you. I recognize that we're almost at time here, but I want to end on one last question for each of the speakers that maybe you can address in turn. We've been talking a lot about, challenges, but I think, there's also a lot of reason to be optimistic that, advanced battery technology is going to be, our future, and will help the United States and some of our friends and allies and the rest of the world, really encourage more EV adoption and, make EVs even better. So I'd love to start with you, Selena, and then maybe go to Kurt, Mike, and then finally Jessica. What are you optimistic about in this space, and what does the audience need to know?
Oh, I'm optimistic about the whole space. I mean, we've shown we can do this, right? And there's so much opportunity. There's so much opportunity. There's so much opportunity for remaking our industry, especially in the United States. So much opportunity for remaking the world, to make, batteries are basically containers for energy. And, if you've got solar or something, you've got it abundantly somewhere, but you need to be able to use it somewhere, and a battery is that container for that energy. Being able to have that everywhere and change really the world's standard of living by having energy that's available for people. I mean, as an engineer, what better mission, right? And it's so great. This is a great thing to be working on.
And Yeah, and Selena and I worked on it together for many years, and I predate that with. I got in the battery industry in 1991, so I've been in it over 30 years, and I joined in NiCad, nickel metal hydride, when that was still king of the market. And I am super optimistic because in all of my years, when I'd go to parties before, and I said I was in the battery industry, you were just relegated to the corner section of the cocktail party. Now you go to parties and you're the center of attention. Everybody wants to know what's going on in the battery industry. So there's a lot of interest, and that is reflected. And what's happened with that is that now there's money in the industry, and that's huge. You get money in the industry, and you get young people that are entering the industry. They're entering into as researchers, and so you get this, which is really a huge difference. And then the biggest thing that's driving all this is the demand. And we have demand. We have domestic demand, and the battery industry went over to Asia because we didn't have a demand. We weren't making the cell phones. We weren't making the laptops. We weren't making the power tools that required batteries. Now it's totally different. We're making the vehicles here domestically. I mean, the battery industry went to Asia because that's where the market was. The battery industry is going to come to the States, and it's going to be built in the States because that's where the market is now. That's what Tesla proved. We had the market here, so we were going to build the cells here, and GM's going to do the same. And then IRA is just another reason that it just is really exciting, because it's really adding a boost to it. We're just getting much more interest from our customers now. They're telling us they need U.S. anode production. Well, we're providing that. So I'm optimistic for all those reasons.
I love that you're the life of the party now. Mike, on to you next.
Well, I guess, I'm the car company guy, so I got to say the products, right? Electric vehicles are fantastic products. I am so excited about the portfolio that we have today, the portfolio that we have in the future. At GM, we have this legacy all the way from the Volt to the Bolt EV and the Bolt EUV to, we're really going to have a full portfolio at the end of this year in high volume segments. They're a blast to drive. They look great. They can serve as a backup to your house if you need it. We can help kind of do some things from a vehicle to grid standpoint. So I'm most excited about the products, getting these more into the, call it, mass market areas, and just increasing adoption.
And finally, Jessica, take us home.
All right, thanks. So it's really exciting, even in the past 5 years, to kind of see the evolution of this industry. So 5 years ago, if you went to a conference, there were not really any talks on battery recycling. It wasn't around. And at Argonne, I work in the materials recycling group. So not only batteries, but e-waste and plastics and things like that. So really seeing the shift of people wanting to be responsible for what they're producing, I think it's really exciting. And I really am excited for the EV transition going forward.
Well, thank you all so much for your time today, and thank you to everyone in the audience for joining us. I apologize we weren't able to reach all of the questions, but please, feel free to follow up with us after the event, and we're happy to connect you with some of our speakers if need be. But thank you all again, and I hope you enjoy the rest of your afternoon and have a sense of optimism about where we're going with advanced battery technology, now and in the near future. Thank you.
Thanks.
Thanks.